Good afternoon. This talk is joint work with Jamie Shield and Ramesh Raskar, my colleagues from MIT. So the title on the program is pretty long, so I shortened it, but the sentiment is pretty simple. In computer vision and graphics, we often deal with simplifications of light transport. So if I take a laser pointer as a ray as it travels through space. But of course, in real life, light is an electromagnetic wave. But to exploit the sort of wave characteristics of light, it's difficult because the wavelength is on the order of hundreds of nanometers, but the macroscopic scenes we deal with in computer vision are on the order of meter size. So what we did is we created a macroscopic time-of-flight camera that incorporates wave theory to accurately improve the task of 3D sensing. So let's take an example. A 3D camera ordinarily, it acquires a single depth per pixel. So here at each pixel, this camera acquires multiple reflections. The depth from the glass window and the depth from the boxes behind. It can also work on long-range scenes without having to resort to phase unwrapping. And of course, it has competitive performance at SNR levels. And so what I think is really interesting in computer vision will be how we start to incorporate wave phenomena into our traditional tasks. So for example, last year at ICCV, we were looking at how to use the wave phenomena of polarization for the pretty mundane task of 3D imaging, pretty classic task of 3D imaging. And today what we're going to do is we're going to use wave phenomena to create multi-depth 3D cameras. Okay, so let's say we have a scene. And going back to computer vision, let's just look at this toy problem. We have a meter-sized scene and we've got two light bulbs. If I turn on one light bulb, I can write the irradiance at a scene point as the irradiance as a function of light bulb A. Okay. Now, if I turn off light bulb A and I turn on light bulb B, my irradiance is that of light bulb B only. But what would happen if I turned on both light bulb A and light bulb B? Well, the answer is a little bit anticlimactic because the received irradiance at the scene point would just be the summation of the individual irradiance of A and B. But where this becomes interesting is if you replace the light sources, ordinary bulbs, with laser pointers. Now if you write the irradiance where the laser pointers collide at that scene point, you get A plus B, but also a cross term of interference. Because every photon that comes from the laser pointer sort of obeys the law of coherence. And you have destructive and constructive interference at that scene point. And this relatively sort of simple term, this interference term, a little detail sort of in how we add these lights, is really the backbone of a very traditional topic in optics of interferometry, where people intentionally superimpose light to get scene clues. Interferometry, for path length interferometry, you might use a reference to probe the scene. So your reference signal would be, sinusoid, and the sample, the signal that reflects off the sine wave, reflects off the sample, would have a phase delay. Now the problem is that this occurs at nanometers. When you use optical light, these are nanometer shifts. And so it's really great for biomedical applications like corneal OCT, but such instrumentation is really specialized, expensive, bulky, and requires a trained operator. If you really want to take this to an extreme, I can underpin the point by bringing up the LIGO project, the recent LIGO project that made waves for its gravitational wave detection. So you can measure sample deviations less than the size of a proton with this technique. That's pretty amazing. But to do this, you need a 4-kilometer interferometer. Okay. And so you could say maybe smaller the measurement, bigger the instrument. And that's not what we want in vision, right? We want a small device that works on a large scene, meter-sized scene. And so if we look at optical phase, you're dealing with, again, nanometer phenomena. So, you're pretty much stuck there. You need to solve that problem by resorting to a different type of wave and look at interference of that. So we're looking at interference with respect to the kinect, which is using electronic phase. So we're going to define some terms here. Primal domain is the frame a signal is sampled in. Dual domain is the frequency transform with respect to primal. And when I say phase TOF, I'm referring to sort of Kinect-style TOF cameras. So a phase TOF camera works as follows. You have an integrated light LED and a camera sensor on the board. And so the light strobes in some sort of reasonable pattern, like a square wave or a sine wave. And when it comes back, there's a phase delay. And that phase delay is easily related to the distance, with the variables of the speed of light and the modulation frequency also encoded. Now, if I were to make this really concrete, we can jump back to sort of undergrad DSP. If I have two signals in MATLAB and I want to get the phase difference between them, there's many ways to do that. But one of the robust ways is to take the cross correlation of the two signals, take the frequency transform of the cross correlation function, and look at the angle of the fundamental. Okay. And so this is sort of summarized on this block diagram. In phase TOF, the reference signal, I've removed all the constants for clarity. It's basically cosine ft. And the phase TOF sample is cosine ft plus phi. So there's that phase delay due to the path length. All right. And so now we cross-correlate them. And this is happening on the chip of the camera. You cross-correlate. And now you have cosine ft plus f tau plus phi. So now the primal domain has changed to tau. And so I can just compute an FFT with respect to tau and take my angle of my fundamental, and then I'm done. And that's phase TOF. But the challenge is that with existing phase TOF, you have these problems of like multipath interference, phase wrapping, and low SNR. Right? Multipath interference is that problem I mentioned in the beginning where you have a glass slab in front of those boxes. You get reflections from both objects. And so in computational TOF imaging has been one of the most exciting areas, in my opinion, in computational photography. I think there's like 30 papers in the last few years. Many people have attempted to solve these problems using various techniques, but all these techniques, typically their common element is they use the same primal domain. They use the same architecture of the Kinect, which is they sample different correlation shifts. And so we're going to try to change that. So how would we do that? Here's the standard phase TOF. This is the chip, this is the readout that comes from the sensor, cosine f tau plus phi. So what we're going to do is remember that we know that phi is related to the z distance and the modulation frequency, so we can just substitute that in. And all of a sudden we realize that it's almost trivial, but the correlation function is now parametric by tau and the modulation frequency. Okay. Now, without loss of generality, we can pick just one value of tau. Let's pick 0 for clarity. And now if we simplify, we end up with a simple cross-correlation that is just parametric in frequency. And if we remove the constants, we're basically looking at cosine zf. So if we sample different values of f, the frequency, then we can just find the frequency of that waveform and get the path length, right? So the primal domain here is modulation frequency, and the dual domain is the frequency transform of modulation frequency, which is why I use that primal and dual notation. Okay, so here's a visual example. I have an object, when it's close to the camera, I have a camera with different LEDs, they're strobing in different frequencies. Okay. When the object is close, if I plot the received signal off the chip with respect to modulation frequency, I see basically a sinusoidal pattern. The frequency of that sinusoid varies with the distance as expected. And this is not new. This is exactly the principle used in frequency domain OCT. Okay, but in OCT, that basically instead of modulation frequency, you have wavelength, optical wavelength. So that's really tailored toward microscopic scenes. So if we were to look at a macroscopic scene, we have a long-range scene here, 3.5 meters roughly. And if you do standard Kinect, you'll see this phase wrapping, right? Where the phase wraps at about, 3.3 meters. So with the frequency domain time of flight, you can see that there's no wrapping. It's sort of inbuilt because there's no concept of phase that you're sampling. The frequency just goes higher. You can look at a multi-depth scenario. This is the example from the beginning where we have that glass slab in front of the boxes. And so if we look at a standard Kinect, it gets sort of confused because you have the reflection from the glass vase, from the glass slab, and the reflection from the box behind. So that leads to an error about 50 centimeters, 63 centimeters. And with the frequency technique, because you're basically sectioning, just like OCT, you're sectioning your scene, you're able to get an error of only just 5 centimeters. You can resolve multipath interference. So for example, if you have a pretty mundane scene, like this ordinary chair, it turns out that this chair has interreflections within it. And so if you do ordinary phase TOF, your error becomes quite high. And you can reduce that by a factor of 2 by just using this frequency TOF. Same measurements, you're just changing the primal domain, sort of rethinking the architecture a little bit. So one of the great things about when you draw from optics is I think they do a lot of good work with analyzing the limits of their system, just like we do in our community as well. And so here we can provide bounds on how close the reflections can be to separate them out. Right? So for example, we can say that multipath interference can be resolved if the path length difference is less than 0.6 roughly times the speed of light divided by the frequency bandwidth. So how many frequencies you sweep. The more frequencies you sweep, or the wider the range of frequencies you sweep, let's say from 10 megahertz to 1000 megahertz, it gets better. And so you can look at the axial resolution here, and you can see that the theoretical and empirical bound sort of agree. Now, how about analyzing multipath estimation in low SNR? So multipath estimation is not new. There's been a lot of papers on this topic in the last few years, but by using this sort of frequency sweep only architecture, you can see that compared to a state-of-the-art method, this is by Ayush Bandari, Ayush is my office mate as well, so he does a lot of multipath separation, and his most recent, we compared his most recent approach, and at low levels of SNR is really where it makes sense to do this frequency sampling, where you can start to see that actually this frequency method offers a better alternative than phase. So, I mean, it's not really about the camera architecture or this paper, but I think it's a little bit of a broader vision, is that we want to sort of formalize the link between how we can bring wave phenomena up to the scale of meter scale optics. And this is one example. So we've changed the primal domain to frequency instead of phase, and that gives us sort of ingrained multi-depth cameras, low SNR, and long-range 3D. So I'd really like to thank my collaborators because they always push me to be better. And Jamie Schill in particular did a lot of the work here with the hardware. Thank you.